Okay, so this is our second day of notes, and welcome to algebra. Most of the problems that you're going to run into in this section, it's just algebra. I'm saying that's kind of cruel though, because it's algebra that you've never really been directly taught before. So these are all principles that you know, and the challenge is trying to identify what you're looking at. So the real topic today is indeterminate forms and removable discontinuities. So we talked a little bit about this in the last set of notes, and today we're just going to work on manipulating limits. So an indeterminate form is when we end up with one of these uh, four forms when we are evaluating a limit. So 0 over 0, or any form of infinity over infinity, whether it's positive or negative. Okay, so these are indeterminate forms, and these cannot be evaluated by directly plugging a C value in. So C value just means any constant. So in the last set of notes, we plugged in numbers to get limit values. So these can't be determined by that. And if you get something like 1 over 0, 2 over 0, any number over 0, this is not an indeterminate form. It actually means something else, which we'll talk about in a second. And we're just going to work on a couple of these from yesterday's notes. So when I work through these problems, I am writing down what I would expect you to write down when you're completing homework. So notation's really important. So please follow the notation as I do it when you complete your assignments. So this first example is from yesterday's notes, as it says. We did it, I believe the limit value was -1, but we looked at a table to find that, and then we looked, actually we didn't look at a graph for that one, but we just looked at the table. So if you plug in a -3, you get 0 over 0. So this is one of your more basic ones. You should always be able to manipulate it to get that limit value. So in this case, it's just a factoring problem. If we factor the numerator, we get x plus 2 times x plus 3 over x plus 3. And since one of those was a factor, we can cancel it. And at every step of this, you're going to try to plug in the number given. So if we cancel those, we can directly evaluate the limit now. It's -3 plus 2 or -1. So it's just like what we did yesterday, but now we're showing it algebraically. So this next example, so we're looking at this one. I'm used to pointing at a board, so it's been hard to adjust to circling things or drawing pictures around them. So in this limit, we have a cubic in the numerator, and we have to somehow evaluate this. So I'm going to plug in the -1, and just like the last one, I get 0 over 0. And so it's indeterminate, which means I have to do something else to evaluate it. And here's an easier way. If you see a polynomial in the numerator, and it's not one you recognize like the quadratic, you can factor it using synthetic division. So we're going to look at this as x cubed plus 1 divided by x plus 1. And I'm going to use synthetic division because it's fast. In the numerator, we have 1x cubed, 0x squared, 0x to the first, and then we have a constant of 1. And the factor we're testing is x plus 1, so we're going to flip the sign and put a -1 out here. Okay, so I'll run through this. So drop the 1, multiply, so it's -1, drop the -1, multiply, 1, -1, and 0. So it is a 0, which means that x plus 1 is a factor of x cubed plus 1. And so that translates to this. Our factor was x plus 1. I'm pulling that from this number. And then this bottom row, if you don't remember, it's just one exponent reduced. So in the first one, you'd have x squared. Next one you'd have x, and that last one would be your constant of 1. So what we just did was we factored x cubed plus 1. And so now I rewrite the limit. And this would be x plus 1 times x squared minus x plus 1. And that would be all divided by x plus 1. So similar to the last problem, we have a factor that's common, we cancel. Now we can plug in the negative 1. So we would get negative 1 squared minus negative 1. So it'd be 1 plus 1 plus 1, or 3. Okay, so those are two types of manipulations that really are just factoring. So if we go to our next example, always plug the number in first, because if you get a number, you're done. But if we plug it in here, we would get 1 squared plus 1, which is 2, and in the denominator, we would get 0. So this one is not indeterminate. Okay, so not indeterminate. The limit does not exist. So if you were to be asked to do this question, you just really write D and E after you showed the step of 2 over 0. So the limit does not exist. What this does mean is that, so I'll write this out, means there is a vertical asymptote at x equals 1. And we'll talk more about that type of limit later. Okay, if we look at this next one, I'll keep red. Plug in the 5. I get 5 minus 5, which is 0. And in the denominator, I would get 5 squared plus 5, or 30. These are typically translated, no matter how many times I repeat this, it's translated as all sorts of things. Indeterminate, does not exist, everything but 0. So if you get 0 over a number, that is just equal to 0. If you get number over a 0, the limit doesn't exist. Okay, so that limit value is just 0. Okay, our next example. Just like all of the other ones, these are really just based on algebraic manipulations. So for this one, I'm going to take a little more time explaining why this is instead of just running through it. Well, let's plug this number in though. So if we look at 4 plugged in, we would get 0, because it'd be root 4 minus 2, which would be 0, and in the denominator 0. So we've shown that it's indeterminate, so now we have to manipulate it. So in previous classes, you've worked with differences of squares. So if we have all of these differences of squares, let's factor each one. So the first one would just be x plus 1 times x minus 1. The second one would be x minus 2, or plus 2, doesn't matter which order, times x minus 2. Last one would be x plus 6 times x minus 6. So differences of squares are pretty simple when they're both perfect squares. So you have an x squared and you have a number that is a square, perfect square. But if you look to the right, so if you look at this side, all we did was take the square root of each term in 2 different parentheses with different signs. So anything that's of the form something squared minus something squared, it actually doesn't have to be squared, but anything that's in the form of number minus number could be treated as a difference of squares. So in this case, what we're really going to look at is this x minus 4. Okay, so based on the 3 examples we did above, the x squared minus 1, x squared minus 4, and so on, this can be factored as root x times root x, and then plus 2 and minus 2. And if you multiply this out, which if you can't see this exactly, you should multiply it out because you'll see that it's just like the ones above where the middle term cancels. So if we have root x times root x, that just gives me x. If we have root x times negative 2, that's negative 2 root x. Positive 2 times root x is 2 root x. And then the last one is 2 times negative 2 or negative 4. So these all cancel and you are left with x minus 4. And the reason we want to do that to this limit here is to expose the common factor. So we have root x minus 2, and then we have our factored form of x minus 4. And just like all of the other ones, we can cancel the common factor, which is that. And I'm going to rewrite this one just to highlight you do need to be aware that you have to keep the 1 in the numerator, and then it's root x plus 2. Plug in the number if you can, which we can, and this would just give us 1 over 4. Okay, our last example is another algebraic manipulation. For this one, I'm not going to plug in the 2 directly because I can already see that it's not going to show me a clear indeterminate form. So the first thing I'm going to do with this one is manipulate it. So in the numerator, I'm going to try to find a common denominator. So on the left side, this does not have the 2 that this 1/2 does. So multiply by 2, and on the right, this doesn't have the x. So now I'm going to simplify it. So the limit as x goes to 2 of 2 minus 1 times x, which is x, common denominator of 2 times x. That's all divided by x minus 2. So can I plug the 2 in yet? I could, but again, it doesn't show me something clearly. So what I'm going to do with this one, I'm going to go to the side here, and I'm going to write out this fraction 3 over 4. If we look at 3 over 4, if I were to ask, can you factor the 3 out of it? You can. So you would say this is 3 times 1/4, right? And that would give you 3/4 if you multiplied it out. I also could write this as 3 over 1 times 1/4. And then if I wanted to multiply it back in, this is going to seem a little ridiculous, but I could say that's 3 over 1 divided by 4, times 1 divided by 4. So another way to write 3/4, if you just follow this logical pattern down, you could write it from 3/4 to 3 over 1 times 4. So if I put parentheses around this, I'm doing this all for a purpose here, it seems long-winded, I could really factor the fraction 3 over 1 out front of the 3/4. So if I go over here, I'm going to just apply that same principle. My numerator is a lot messier. It's 2 minus x divided by 2x. But I can factor that out without having to think about the whole flipping fractions and multiplying. Just look at it as one item, take it out front. So I've factored it out of the fraction, and now I'm left with 1 over x minus 2. Okay, so this little part here, I don't remember where I first identified that, but when I really looked at that, it helped this fraction stuff become a lot clearer. So in this limit now, can we plug in the 2? Yes, but it's going to give us, now it'll give us a indeterminate form. So this will give us 0 over 0. So we've now gotten to the indeterminate form. So what we can do now is if we look at this 2 minus x and this x minus 2, they only differ by a negative sign. So what I'm going to do is factor out the negative sign. Doesn't matter which side you do it to, it's going to have the same result. But if I take it out of the 2 minus x, I would then have negative times, and I'm going to switch the terms around so it looks the same, x minus 2 over 2x times 1 over x minus 2. Okay, so now we have that same situation we've had in every problem where we've identified a common factor, we cancel it. Can we plug in the 2 now? Yes, we can plug this in, and it is going to be negative 1 divided by 2 times 2, or negative 1/4. Again, if you have any questions, make sure to email me or attend our Google Meet sessions. Thanks.